Welcome to AI Paper Podcasts. Today we're diving into something super relevant for, well, the future of driving. We're looking at how to make AI in cars, specifically those complex deep learning tasks, run efficiently without draining the battery or, more importantly, missing critical deadlines. The paper is Sequential Task Assignment and Resource Allocation in V2X-enabled Mobile Edge Computing. And if you're working anywhere near autonomous systems, V2X, or edge computing, you'll want to stick around. This tackles a really core problem, AI tasks that have steps. You can't just do them all at once.
Exactly. Think about object detection using a deep neural network. Each layer depends on the output of the previous one. You can't just parallelize everything arbitrarily, and the challenge is huge. These tasks are computationally heavy, they need answers fast. We're talking maybe hundreds of milliseconds, and they're running in cars that are moving, connecting, disconnecting. It's dynamic. Plus, there's the energy cost. You can't just crank the processor to max all the time.
Okay, so for a quick takeaway, that first-minute summary, what's the absolute core idea here? These researchers figured out how to handle these sequential tasks, minimizing energy use while guaranteeing they meet those tough deadlines, that TN max they call it.
They do it with a smart two-tier system. Tier 1 is vehicle-to-vehicle, or V2V. They've got a really efficient way to match needy vehicles with helper vehicles nearby. It uses the Hungarian algorithm for the matching part, and crucially, they combine that with optimizing the communication and computation resources together. Analytically, it's fast.
Okay, NV to HV matching, joint optimization. Got it. What's Tier 2?
Tier 2 is the backup when V2V doesn't work out. That's vehicle to infrastructure, using roadside units or RSUs. Here, the big problem is multiple cars trying to use the same RSU. It's like everyone trying to get Wi-Fi at a busy cafe.
Ah, the multi-access competition problem.
Right. And they tackle this with a neat two-step optimization method. It figures out how to share the RSU's bandwidth, the subchannels, and its computing power really effectively. It finds a near-optimal solution without getting bogged down in complexity.
So, minimum energy, meets deadlines, handles sequential tasks, and works in both V2V and RSU scenarios. That sounds pretty comprehensive.
It is. It really tries to provide a complete framework.
All right, let's dig into the details then. First up, that's the system model. You mentioned 2 tiers. Can you paint a picture for us? Like, what does Figure 1 in the paper show?
Sure. So picture the road. Tier 1 is basically cars talking directly to each other. You have a needing vehicle, the NV, that has a big task to run. It looks for nearby idle vehicles, IVs, that aren't busy. If it finds one that fits the criteria, that IV becomes a helping vehicle, an HV, direct V2V communication.
Okay, simple enough. Car helps car. What about Tier 2?
Tier 2 is when that VTV Link isn't feasible, maybe no helpers are nearby, or the connection's bad. So the NV then reaches out to a roadside unit, an RSU. These are like small servers installed along the road, part of the infrastructure, V2I communication.
And these RSUs have MEC servers, mobile edge computing.
Exactly. They have processing power. And a key thing the paper highlights is that these RSUs are connected to each other via high-speed wired links.
Wired, not wireless between RSUs.
Right. That's important. It means if a task is too big for one RSU, or it makes sense to split it, multiple RSUs can collaborate very quickly and reliably without worrying about wireless interference or channel quality between them.
Okay, that makes sense. So the backbone is solid. Now, what about the tasks themselves, the sequential dependency thing? Figure 2, I think.
Yeah, Figure 2 shows it well. Think of an application not as one big job, but a chain of smaller subtasks. Let's say Secti Sexian Mahler is the M-Seth subtask of application N. It can only start after the previous subtask, Sexian, is completely finished, and its results, the output data, Neil Muller, have been received. It's a strict one-way street.
Like an assembly line. Step A finishes, passes the part to Step B.
Exactly. And they make a key observation about that intermediate data, the Neil and Muller. For many AI tasks like object detection, the result of a step isn't huge. It might just be coordinates for a bounding box or a classification label.
So the data being passed along the chain is small.
Generally, yes, and this leads to a core design principle: minimize wireless hops. The initial data upload happens once, either NV to HV or NV to RSU. After that, if the task is further broken down and passed between HVs or between collaborating RSUs, that transfer uses the reliable wired links.
So you avoid sending lots of intermediate results over potentially flaky wireless channels. That saves time and reduces potential errors.
Precisely. It tackles the communication bottleneck head-on.
But wait, you mentioned the intermediate data is small. What about the final result getting back to the original car, the NV? isn't there a delay there?
That's a really good point. The paper explicitly states they neglect the reverse transmission delay, sending the final result back.
They just ignore it. Why?
Their justification is that for the target applications, like getting those bounding box coordinates, the final output data is also very small. Tiny, in fact. So the time to send it back is considered negligible compared to the computation and the initial data upload time.
Okay, I can see that for object detection results. But is that always true? What if the task was, say, generating a complex navigational path update? That might be larger.
You've hit on a limitation, or rather a scope condition. If the application's final output becomes significant high-res map chunks, video clips, then, yeah, neglecting that return delay wouldn't work anymore. The model would need extending.
Right, so it works well for current common inference tasks where the answer is compact.
Exactly. It simplifies the math considerably for this framework.
Okay, let's dive into Tier 1 then, the NVHV, Direct Collaboration.
Yeah.
How does a car find a helper? You mentioned matching.
Right, the NVHV matching scheme. The goal is simple. Pair up as many NVs with suitable HVs as possible using nearby resources. It's about efficiency.
How do they decide who is suitable?
There are two main conditions an idle vehicle must meet to even be considered a candidate helper. First, the obvious one, communication range. They need to be close enough, say within 70 meters, for a decent V2V link. Or maybe they're a bit further but catching up fast. If the potential helper behind you is faster, the communication window is opening, so it might still be viable. They account for relative speed and direction.
Clever. So proximity or imminent proximity. What's the second condition?
This one's about capability, the IV computing resource check. Basically, they ask, if this idle vehicle uses its maximum available processing power, can it finish the entire task sequence before the absolute deadline, 10 max day?
A stress test. If it can't even theoretically meet the deadline going full throttle, then it's no use as a helper for this specific task.
Precisely. No point starting a collaboration that's doomed to fail the latency requirement.
So once you have this list of candidates that are close enough and powerful enough, how do you do the final pairing?
That's where the Hungarian algorithm comes in. It's a classic optimization algorithm used for assignment problems. Given the set of NVs needing help and the set of qualified IVs ready to help, it finds the optimal one-to-one mapping that maximizes the number of successful pairings. It avoids weird situations like pairing a really demanding task with a barely capable helper if better options exist.
Okay, so matching complete. Now the NV and HV are paired. What's next? Minimizing energy.
Yes. Now we hit optimization problem P1. The goal is to minimize the total energy consumed by both the NV and the HV, combined with some weighting possibly. But this minimization is subject to constraints. The big one is the total delay. The V2V transmission time plus all the computation times for the subtasks must be less than or equal to 10 max.
And there are limits on how fast the CPUs can run, presumably.
Right. The allocated CPU frequency for any subtask on a vehicle can't exceed the vehicle's maximum frequency, 5 hours.
This sounds complex to solve quickly in a moving car, lots of variables.
This is where one of the key mathematical insights comes in. They show that if you fix the offloading decision, meaning you decide up front which specific subtask is the first one, the HV will handle the problem transforms.
Transforms how?
It becomes a convex optimization problem, and this is huge.
Why is convex optimization so important here?
Because convex problems have a wonderful property. Any local minimum is also the global minimum. And even better, there are very efficient algorithms to find that guaranteed best solution. You don't get stuck in suboptimal traps.
Okay, so it guarantees the best energy saving for that fixed offloading decision. But does efficient algorithm mean fast enough for a car making millisecond decisions?
Yeah.
I saw mention of the Lambert W function. It sounds, well, intense.
It sounds intense, but the beauty is that it allows for an analytical solution. They can derive the optimal settings using mathematical conditions. It's Karush-Kuhn-Tucker or KKT conditions. The Lambert W function, tubular fibrix pops out as part of the formula for the optimal V2V transmission time. Tau thon. It's complex math, yes, but it gives a direct formula. You plug in the numbers, you get the answer. No slow searching or iteration needed at this stage.
So it's like having a direct equation, even if the equation itself looks complicated. Calculate once, get the optimal time.
Exactly. That analytical nature is what enables the speed needed for real-time application.
And this calculation also gives the optimal CPU speeds, right? The tau thum, the UBA. You mentioned Lambda and Kappa. What are those?
Right. The optimal CPU frequency for each subtask, VEIM, depends on these two key factors. Lambda is the Lagrange multiplier associated with the delay constraint. You can think of lambda as the shadow price, or the urgency factor of meeting the deadline max. If the deadline is really tight, lambda will be high, pushing the system to use more resources, like higher frequency. If the deadline is loose, lambda is lower.
Okay, so lambda represents the time pressure. What's the kappa?
Kappa's is much simpler. It's just a coefficient representing the energy efficiency of the specific device's CPU. How much energy does it cost to run one computation cycle? Different hardware will have different kappa values.
So the optimal frequency is a trade-off between the urgency and the hardware's inherent energy costs.
Precisely. It's a mathematically derived sweet spot.
Okay, Tier 1 sounds quite elegant with that convex optimization trick. But what if Tier 1 fails? No suitable helpers nearby. That brings us to Tier 2, the RSU Collaboration.
Exactly. Tier 2 is the safety net, using the roadside infrastructure. But as you hinted earlier, it brings its own major challenge: multi-access competition.
Right, multiple cars all trying to talk to and use the same RSU's resources.
Yeah, unlike V2V, which is mostly one-to-one, an RSU might be serving several NVs simultaneously. This leads to optimization problem P2. And P2 has even more variables to juggle. You still have the offloading decisions, which RSU handles which subtask if multiple RSUs collaborate, denoted error RBA. You have the V2I transmission delay, TON. You have the CPU frequency allocations on the RSU server, PHY RLAs.
And the really tricky one seems to be sharing the wireless bandwidth, right? How many communication subchannels, what dollars does each vehicle get?
That's the kicker. Bub the dollars has to be an integer. You can't allocate 3.7 subchannels to a car. And optimizing with discrete integer variables is generally much harder computationally than with continuous variables.
Why? What makes integers so difficult?
Think about it. With continuous variables, you can often use calculus, find derivatives, find smooth optimums. With integers, you suddenly have jumps. You might have to check lots and lots of combinations. If you have, say, 100 total subchannels and 10 vehicles, the number of ways to distribute those integer channels is astronomical. You can't just check them all.
Okay, so brute forcing the integer subchannel allocation is out. How do they solve P2 efficiently then?
They use a really clever two-step strategy specifically for the subchannel allocation. It's designed to get close to the optimal integer solution without the massive computational cost.
A two-step approach. Let's break that down. What's step one?
Step one. Pretend the problem is easier than it is. They temporarily treat the allocated bandwidth for each vehicle, B dollars, as a continuous variable. Remember, B dollars is just the number of subchannels, but times the bandwidth of one subchannel, B dollars. So they relax the integer constraint and solve the resulting continuous optimization problem. They use an iterative method, again leveraging convexity where possible, to find the theoretically optimal continuous bandwidth allocations, beta dollars, along with the corresponding optimal delays, TON, and RSU frequencies, for dollars.
Okay, so step one finds the perfect theoretical answer, assuming you could allocate fractional channels, like finding the ideal point on a map, even if it's in the middle of a field.
Perfect analogy. That's exactly it. Now, step two, find the closest real spot.
The nearest integer solution.
Right. Since the subchannels dollars must be integers, they can't just use the fractional dollars directly. So they take that optimal continuous point dollar, which lies on the plane where total allocated bandwidth equals total available bandwidth, some BN, ELN, B boiler, and they perform what they call adjacent integer point searching. Essentially, they look at the integer combinations of the dollars that are immediately surrounding the continuous optimum dollar. They check just these few nearby integer points to find the best feasible integer solution.
So instead of searching the entire vast space of integer combinations, they use the continuous solution to guide them to a very small, promising region of integer possibilities, and just check those.
Exactly. It dramatically prunes the search space and gives a near optimal integer solution very quickly.
That's smart. What about the other decision which RSU handles, which subtask, the enerdazers? How's that decided?
That part they mentioned is handled by enumeration, basically checking the different possibilities.
Doesn't checking all possibilities become slow if there are many RSUs and many subtasks?
It could in theory, but they make a practical argument. In a real-world scenario, a vehicle is likely only going to interact with or offload tasks across maybe 2 or 3 nearby RSUs, not every RSU in the city.
Okay, locality helps.
Right. If you only consider, say, 3 RSUs for collaboration, M3, the number of ways to assign the subtasks among them is manageable. They estimate the complexity around OSM to M, where N is the number of NVs. For small m, this is computationally feasible within the required time limits.
Got it. So clever continuous to integer mapping for bandwidth and practical constraints keeping the RSU assignment manageable. This all sounds great theoretically, but does it actually work? Let's talk results. How did this proposed method stack up against others?
The results are pretty compelling, especially looking at figures 3 and 7 in the paper. They compare their method against several baselines, including ones that always offload FOM, ones that only compute locally, POM, and others. The key finding is that their proposed method consistently achieves the lowest average energy consumption, the AEC. And critically, its advantage becomes more pronounced when the delay requirement, TMMAC, is tighter.
So when things get tough and deadlines are strict, their optimization really shines in saving energy.
Exactly. And there's a clear reason why, which is maybe the most important practical insight.
Yeah.
Look at the methods they compare against, like FOM, POM, BFM. Many of these simpler strategies tend to rely on using the maximal CPU frequency whenever computation is needed, just to be safe with the deadline.
Just run as fast as possible.
Yeah. But the physics of processors is punishing. Computation energy consumption, as we discussed with Kappa, is roughly proportional to the square of the CPU frequency, Kappa C F22.
Ah, the phi-to-2 relationship. So doubling the speed doesn't double the energy, it quadruples it, roughly speaking.
Precisely. So those methods that just blast the CPU at max speed, even if only for short bursts, end up consuming way more energy overall compared to this method, which carefully calculates the lowest possible frequency needed to meet the deadline.
That makes perfect sense. It's the cost of being lazy and just using max speed versus doing the math to find the optimal speed.
It really highlights the value of that joint optimization. They also show how relaxing the deadline helps. If you give the system more time, increase tolerance max, it can afford to run the CPU slower.
And slower means significantly less energy due to that FEV22 factor.
Exactly. A looser deadline translates directly into substantial energy saving.
What about other factors like the VTV communication quality? Figure 5, I think?
Yeah, Figure 5 looks at the V2V link. If you have higher V2V bandwidth, B2V2VV, data transfers faster. This reduces the transmission delay part of the total time. Less time spent transmitting means more time available for the computation part within the same overall telemax.
And more time for computation means?
You can run the CPU slower. So higher V2V bandwidth actually leads to lower overall energy consumption by enabling slower, more efficient computation. It's a nice interplay.
That's fascinating. Better communication saves computation energy. What about distance?
Greater distance generally increases energy consumption, mainly because the wireless signal weakens, path loss, forcing the vehicles to use higher transmit power to maintain the link. Though they note transmission energy is still usually less dominant than computation energy overall.
Okay, and Figure 6 looked at the capabilities of the vehicles themselves.
Right. It showed that the closer the computing capacity of the needing vehicle, NV, is to the helper vehicle, HV, the lower the total energy.
How did that work?
Well, if the NV is already quite capable, the HV doesn't have to pick up as much slack or run its own CPU. It's hard to meet the deadline for the offloaded tasks. It leads to a more balanced, lower energy collaboration.
Interesting. And subtask structure. Does how you break down the problem matter? Figure 4.
It does. Generally, they found that dividing the main task into a larger number of smaller subtasks tended to decrease the energy consumption in Tier 1.
Why would more steps be better?
Because it gives the optimization algorithm more granularity, more flexibility in deciding exactly where to make the offloading split between the NV and HV. More options allow it to find a slightly better energy-saving balance point. But this only helps if you're using their optimal offloading strategy.
Makes sense. And finally, what happens in Tier 2 when more cars pile onto the RSUs?
Predictably, the average energy consumption goes up as the number of NVs competing for RSU resources increases. Even with the optimal allocation, if you have more vehicles sharing the same fixed bandwidth and RSU processing power, there's just more contention. The system might need to nudge frequencies slightly higher for everyone to meet their deadlines. The optimization minimizes the increase, but some increase is inevitable with more competition.
Okay, so let's wrap this up. This paper really seems to deliver a solid, mathematically grounded approach for a critical problem in V2X. We've got this multi-tier architecture handling both V2V and V2I, smart ND-HV matching using the Hungarian algorithm, and then these joint optimization solutions leveraging convexity and KKT conditions to minimize energy while hitting those hard sequential task deadlines.
Absolutely. The key is finding that analytical or near analytical solution, like using the Lambert W function or the two-step RSU allocation. It avoids complex, slow searches and guarantees optimality or near optimality, which is vital for real-time V2X. The focus on minimizing energy by optimizing frequency, not just using max speed, is crucial.
It really feels like a practical blueprint. Which brings me to a final thought for our listeners to chew on. The power here comes from those fast analytical KKT-based solutions. They rely on knowing things like the current channel state, the workload, and calculating parameters like that urgency factor lambda very quickly. The paper uses iterative methods for some parts, especially in the RSU tier.
Right, those parameters need constant, rapid updates in a dynamic environment.
So here's a thought. The paper compares against some RL baselines, but what if you didn't just compare, but integrated? Could you use something like deep reinforcement learning, specifically to predict or track the optimal values of those key analytical parameters like lambda, or the optimal continuous bandwidth bolded dollars in real time?
Interesting. So use RL not to replace the KKT optimization entirely, but to feed it the rapidly changing inputs or parameters it needs even faster or more predictably.
Exactly. Could that give you the best of both worlds? The mathematical rigor and optimality guarantees of the KKT approach, combined with the adaptive predictive power of RL to handle the extreme dynamism of vehicular networks even more effectively. Something to think about.
That's a fascinating direction. Merging the strengths of analytical optimization with learning-based adaptation, definitely food for thought.
Well, if you're building these V2X systems, hopefully this gives you a much clearer picture of the energy latency trade-off and how to tackle sequential tasks efficiently. That's all for this AI Paper podcast. Thanks for tuning in.